Hey folks, today in this video I want to walk you through the basic ideas and mathematics of performing a two-sample z-test for the difference between two population proportions. And the key idea here is that there's going to be some proportion for some population, say P1, and some population proportion P2, and we're going to be doing some test of the difference between those. So for instance, let's say we were talking about a variable, and let's talking about, say, we're talking about whether people are left-handed or not, right? And we might want to compare, maybe is there a difference between, say, males versus females in terms of whether they are left-handed or not. So let's say we made as a null hypothesis that the proportion of males that are left-handed is the same as the proportion of females. So I could do something like the null hypothesis would be something like that. P1, actually let's do useful letters. PM is equal to PF, right? Where P equals, PM is the proportion of males, right? That says males, not moles. Terrible handwriting, sorry, Amalia. Proportion of males that are left-handed, and then of course I'd say PF is the same thing for, I'm just being lazy here, for females, right? And so as a null hypothesis, we might say that it's the same. An alternative could be something like, oh, maybe it's not the same. The proportion of males is not equal to the proportion of females who are left-handed. So how could we evaluate these hypotheses mathematically? Well, in the past, we always had as a null hypothesis that something is equal to a number, right? And here we don't have anything equaling a number, but we do need things to equal a number. And so how will we make something equal a number? Well, similar to how we saw with the sampling distribution, let's turn this into a difference, right? I could take this null hypothesis and I could transform it and rewrite it as the null hypothesis is that the proportion of males minus the proportion of females is equal to 0. If they're equal, then their difference should be 0. Same thing then with the alternative. I could say the proportion of males minus the proportion of females is not equal to 0, and that would be a worthwhile alternative. So that's how we'll essentially start off by writing our hypotheses for looking at the difference between two proportions, right? All right, so how would I actually carry out this test? Well, we're going to have to first, collect a sample. And let's say I collected a sample. Let's say, I don't know. Here I'm going to almost make a little table here. Let's say this is my sample data, right? In my sample data, let's say here's the males. Let's say in the males, I surveyed N was, say, just 100 people, and I found X equals, say, I don't know, 12 of them that were left-handed. And then with the females, let's say this time I sampled 115, I'm just making this up, and let's say I found, I don't know, like 17 of them were left-handed, right? And so then I would say, all right, how does this evidence, how can I use this data to help me determine these hypotheses? Well, the first thing I'd have to do is, based on this sample, do I have an expectation of normality? Can this satisfy large counts? So when we carry out a test for a two-sample z-test for the difference between two proportions, we're going to do the large counts condition, right? And the large counts essentially is going to have us just look at our sample and see if we have at least 10 successes and 10 failures, just like large counts always is, in each of our two samples. And here we're actually looking at the exact sample data. When we were doing a one-sample z-test for proportion, we always looked at the number of expecteds. But in this case, I don't really expect anything at all. I don't have an expectation. My only expectation is that the difference between these two things is 0, but I don't necessarily have any expectation about what that proportion is. In fact, notice I don't even care what proportion of males are left-handed, and I don't care what proportion of females are left-handed. I just want to know, is it the same, right? And so I don't have an expectation of how many successes I should have. So I'll actually look at the number of successes and the number of failures in my sample itself. And so in this case, you'll notice that this X really was the description of how many people were left-handed. So in this case, I had 12 people that were left-handed, which left, 88 that were right-handed, or maybe just not left-handed. What would that even mean? I don't know. And then out of this 115, we had 17 that were left-handed. Of course, then what are we doing here? 115 minus 17. I should have done the other way. Isn't that dumb? But whatever. 98 failures there. And so both of those are at least 10. I'm not doing the full formal process here. I'm just presenting the core ideas. So we will have normality. So if we're going to do our math, just like always, we'll calculate a test statistic, right? And when we'll calculate a a p-value. So our test statistic, we will have normality in this distribution, just like we kind of saw with the sampling distributions in another video. But the test statistic, it's going to be a z-test statistic, right? And in this case, that means we're going to have to start off, our statistic is actually the actual difference in p-hats that we had here in our sample. So actually, let's take a look at what proportions we got. Of the males, we had 12 out of 100. Why did I just put that in the calculator? That's obviously 12%. So for the males, before I actually even calculate my test statistic, let me write this down. The p-hat for the male, so I'd say p-hat m was equal to 0.12, right? P-hat female, right, was equal to, let's see what, I'd have to do 17 divided by 115, and here I got 14.78, blah, 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 blah. I'm gonna use the full thing when I do my calculation, but it was about 0.1478. And so I take a look at this. I do have a difference between these two, right? And so whatever the actual difference is going to be the first part of my test statistic. So in general, let me use a different marker, one that you can see a little bit better. I'll use the black one here. So that'll be p hat, in this case, well, I'll write it in general, p hat 1 minus p hat 2. And now, what do I expect that difference to be? I expect that difference to be 0. So technically, I'll subtract the difference I actually got in my two samples from 0. But obviously, subtracting 0 doesn't really change anything. So I wrote it down to be thorough because this is like a z-score. But it doesn't actually matter in our calculations. Now, to get the test statistic, then we'll have to have a big formula for our standard deviation. And just like we saw when we were doing sampling distributions for a sample mean, where do I have those papers? Do I have it here in front of me? Let's see here. Aha! We saw this right here, that this big old honkin' standard deviation formula. We're going to use something very similar here when we're doing our test, right? Except there's going to be a key difference. The way we actually do this is we're going to have a p hat c times 1 minus p hat c over n1 plus p hat c times 1 minus p hat c over n2. And so I'm sorry that I wrote that a little bit small. It's a little tough to read. But notice that I all of a sudden am bringing in here for the standard deviation a p hat c, right? And so here's a bigger version of this test statistic. What I actually am going to be doing here when I calculate this test statistic is I'm going to, even though I didn't have any type of estimate or expectation for that I could use for large counts in terms of my successes and failures, because our null hypothesis says that there's no difference between the proportions in population 1 and population 2, say in the proportion of males that are left-handed and the proportion of females that are left-handed. Since there's not supposed to be any difference, what I'm going to calculate here as p hat c as a big estimate for what that proportion is in each of those populations. If P1 equals P2, then what I'm going to do is I'm going to combine my samples together. This is called a pooled proportion or a combined sample, right? And so in other words, if I said, what's my total sample size? So in this particular instance, my total sample size would be 100 plus 115. So that's like, let's do math. That's like 215, right? In my whole big sample, if I combined all these samples together into one huge sample, I had 215 people altogether. And then how many people were left-handed altogether? Well, if I combined the samples together, it would be 12 plus 17. 12 plus 17 is 29. So an estimate for what might actually be the proportion of left-handed people altogether, if there really is equality in between males and females. And remember, of course, this was PM. If I could write letters, that is just trash. I don't even know why I try. And that's PF. Then our estimate would be something like, again, 29 out of 215. And if I put that in my calculator, that's an estimate of about 13.49%. So in this case, we're estimating 13.1349 as to what that what this proportion would be, and that's actually the number we're going to use in our calculation for our test statistic here. So that's what I'm gonna plug in. If I actually do this calculation, my z is going to equal this difference. And so what's the difference between these two p hats? Well, again, I did 17 divided by 115, that was this, and I'll subtract 0.12, and so the difference is this guy. 575ths, or 0.027826, 0.27826. Now in this case, order doesn't necessarily matter because it's a two-tailed test, and so I don't necessarily have to worry about whether this is positive or negative. But in this particular instance, since I did male minus female here, and this P1 is say male and this P2 is say female, I should actually make this negative because it was 0.12 minus the 0.1478. And so I'll make that as a negative numerator, and that ultimately matters that much. And then I'll do a big square root, and then I'll take our estimate for p hat, which what was it? 0.1349. So I'll do 0.1349 times, what's 1 minus 0.1349? Let me check. Quit. 1 minus 0.1349. I got 0.8651. 0.8651 all over my first sample size, which was 100. And then I'll add to that, because remember we always add variances. I'll add to that the same thing, 0.1349 times 0.8651, all divided by this time 115. And so, my numerator is this tiny thing, but denominator is this enormous thing. Let me calculate that real quick. So that's the square root. It just took me so long to write it down. I'm like sad I have to still type it in my calculator. 0.8651 divided by 100 plus same thing, 0.1349 times 0.8651 divided by 115. And we're with a total of that guy, 0.4670. And so I'm just going to take my old numerator, which was 0.27826, and I'll divide that by this guy. Of course, remembering that it was negative, and so I got a negative 5.957. Right? So this equals negative 5.957. What am I doing? Something doesn't seem right to me. Oh, do you know what I did? I just realized. When I did 0.1478 minus 0.12, that's 0.0278. Oh, my gosh. I was about to say, that z-score was way humongous. I could stop this video and restart it, but no, why would I do that? Let me just, let me redo the calculation. So it was 0.027826 divided by, where was our answer up here? This guy right there. Let's divide. That makes so much more sense now. 0.5957. I was going to say, these two guys were too close for too small of sample sizes for me to get a test statistic that was like 5 point something. So there you go. I'm not even going to cut out my mistakes here. Hope you guys can live with that. I can live with it too. But there's the key idea, 0.5957. So if I actually wanted to evaluate this test statistic to get or use this test statistic to get a p-value, it's no problem. I can just, let me get another piece of paper here, and I'll just put it underneath. So to get an actual p-value, remember this would be a two-tailed test, and so I would, once again, this will end up just being a normal distribution because proportions always deal with normal distributions. If this is standard normal, then here I am with a 1, 2, 3 standard deviations above the mean, and let me draw this guy. This guy had its test statistic at about 0.5957, which would be around there. That's where my z is, and of course, because this is a two-tailed test, I would go on the opposite side, and there's my negative z over here, where of course z was 0.5957. And so which way do I shade here? Well, I'm going to shade both to the left and to the right. Ooh, a yellow marker. I don't know if I've ever used this guy yet. This is maybe the first time. Oh man, it like bleeds a lot too. That's kind of annoying. So this p-value is actually going to be fairly large. So if I go to normal CDF and I do 0.5957 to infinity with a mean of 0 and a standard deviation of 1. I hit enter and I got 27.5 whatever. I'll double that. That's my total p-value, and it's about 55.1%. My p-value would equal about 0.5514. right? So over 55%. It doesn't matter what the level of significance is. I would certainly fail to reject the null hypothesis. So anyway, a little bit more complicated math here, right? The most complicated thing is us having to realize we need to think about the stupid little pooled proportion thing, right? Where, again, it's based on this assumption that the proportion of males, proportion of females is exactly the same, so that we can use that to get a better estimate for the standard error here, right? For our distribution, of course. And this guy here, this guy is going to be a standard error. This is the standard error of p hat 1 minus p hat 2 based on a pooled proportion there. Now, just so you know too, we just did a whole bunch of work calculating this by showing all this work, and that's kind of ugly. I'm really disappointed in the quality of my handwriting, and this is kind of a mess, so I apologize about that. But there was a much quicker way. We could have just done this in our calculator, just like always. If we were to go to tests, right? And since this is a 2-sample z-test for difference proportions, if you go down, you'll eventually see, what do we have here? A 2-prop z-test. And if we just enter in information here, was doing some other work earlier. I just enter in the facts for my sample. So remember, what did we have? We had X was 12 and N was 100. So in the males, I had 12 males out of 100 that were left-handed. And then I had here 17 females out of 115 that were left-handed. And then I made the screen is really blue. It's because I'm doing this at night. I don't have natural sunlight, sorry. That I do a 2-tailed test. I hit calculate and Shazam. Look, boom, right there. There's my test statistic. There's my p-value. And check this out too. Do you see where you see this little, just a p hat? It doesn't say p hat C, but it just says p hat 0.13488. Does that look familiar to us? Heck yeah. That was the pooled proportion. So the calculator will even tell you what it used as that pooled or combined sample proportion to use for the standard error formula here in the denominator of our test statistic, right? So that's very cool. This does the whole thing. 2-prop z-test is definitely the quick way to go. The number one reason why I point this out is because if you're showing your work thoroughly, if you use the wrong values down here in the denominator, well, it's just very sad. You're going to get a test statistic that's slightly off, and your p-value will be slightly off. And not only that, but we'll take off points because we expect you to know the key ideas here. And why do we pool? Again, the key idea is that we're assuming that the proportion based on our null hypothesis is that there's no difference between these things, and since the null hypothesis is that there's no difference, then we can combine the samples to get the best estimate. Okay, so anyway, that's just a quick example of a 2-sample z-test for difference between 2 proportions. We're also going to be learning here about how to do confidence intervals. So stay in touch. Have a beautiful day, and catch you on the flip side.